I was doing some MIT integration B problems earlier today, and through those, I kind of found a way to evaluate the integral of secant of x dx uh, in a very unique manner, I think, and it involves Euler's formula. But before I get into that, I want to show the most common way in introductory calculus classes that the integral of secant of x dx, aka its antiderivative, is calculated out. And the way that it's typically done is shown right here where this arrow is pointing. And what you do is multiply secant of x by this expression, secant of x plus tangent of x over secant of x plus tangent of x, which obviously that expression is equal to 1. So you can do that. And once you multiply by that, you expand it out, make a simple u substitution, and you end up with a basic integral and get this as your antiderivative, the natural logarithm of secant of x plus tangent of, or the natural logarithm of the absolute value of secant of x plus tangent of x plus c, since this is an indefinite integral. And that's fine, but this step right here, secant of x plus multiplying by secant of x plus tangent of x over secant of x plus tangent of x, requires quite a bit of cleverness and ingenuity. It's not at all obvious that you should multiply by an expression as strange as that one. So it's not really a straightforward way to evaluate the integral. So with that being said, I'm going to present this other way that I've basically discovered. I couldn't find much about it online or anything, so I think it's pretty exciting that I came across this, and it involves using Euler's formula. So if you don't know what Euler's formula is, it's e to the ix equals cosine of x plus I sine of x, where I is the imaginary number, aka the square root of -1, and x can vary over the real numbers. So with that in mind, I'll draw a new arrow here, and we can begin to evaluate this integral. So the first thing that you have to realize is that secant of x equals 1 over cosine of x, and this is just standard trigonometric identity. I suppose it's the definition of secant of x. So that means that the integral of secant of x dx equals the integral of 1 over cosine of x dx. And here it's not really obvious where to go. You might be stuck. I mean, there are methods of you can multiply by cosine of x over cosine of x and come to a solution, but that isn't as obvious, I think, as the way that I'm about to show you, and it involves Euler's formula, as I've mentioned, and I pre-wrote over here the expression that we're going to substitute in for cosine of x. And just to show you a bit on how I got it, I didn't just want to put it in. And all you have to do is recognize this is Euler's formula, just in standard form. And then the next line under that is Euler's formula with, in here, I'll make this very clear, it's equal to e to the I negative theta. And that's how we get this part right here, because cosine of theta is an even function, so cosine of negative theta equals cosine of theta, and sine of theta is an odd function, so sine of negative theta equals negative sine theta. So that's where that subtraction sign comes from, and the sign of cosine stays the same. But anyways, you add those two together and basically just rearrange terms, and you end up with this expression for cosine of theta. So you substitute that back in. So now it becomes 1 over, and it's always kind of hard to write these kind of double-decker fractions, but e to the ix plus e to the negative ix all over 2 dx still. We haven't done a change of variables or anything. We're just now moving kind of onto the complex plane. And here I'll just rewrite it like this: 2 to the e to the, or t over, plus e to the negative ix dx. Okay, now you might think, okay, well, we're stuck again. There's not really a way to evaluate this integral, is there? And what you should probably immediately think of, since there's not really much else to do, is to make a u substitution. So that's exactly what we're going to do. And what we're u substituting for is pretty obvious. There's not much else you can u sub for. Like, obviously you can't u substitute for a constant. So we're going to do a u substitution of u equals e to the ix, which would then mean that du equals ie to the ix dx, and that's just standard differentiation of the exponential function. So now we can start substituting in, and I'm just going to bring this 2 out in front just to, because it's a constant, you can do that, obviously. So substitute it in now. So e to the ix equals u, and plus e to the negative ix. Well, I'll write it here just for, and I'll do a new color just so you can see it real clear. E to the negative ix equals e to the ix to the negative 1, which then, hopefully you see that much more clearly now, equals u to the negative 1. Okay, u to the negative 1, and we can't just write du, because remember du is equal to this expression times dx, so we need to solve for dx from this equation to get a proper substitution. So dx equals, and we divide both sides by I times e to the ix, and you'll get du over ie to the ix. So now we can substitute this in for dx, and you get times du over I, and then notice that this e to the, oops, that's kind of big, but the e to the ix part of that is just u, because we have u equals e to the ix right here still. So I times u. Okay, and now we can bring that I out in front because it's a constant and it's being multiplied across. So we have 2 over I integral of du over u plus u to the negative 1 times u. And we expand this out, and then you end up with du over u times u is u squared, and u times u to the negative 1, and just recall that u to the negative 1 equals 1 over u. So if you multiply that by u, obviously there will be a u on top, equals 1. And then from here, this is should immediately ring some bells in your head, hopefully, and you see that this is to the I, and the integral of dx over x squared plus 1 equals arctangent of x. Hopefully you know that. It's just a basic formula that I'm going to take for granted here. I'm not going to prove it or anything, but it's a common integral, and you should probably know it if you don't already. So using that, we have arctangent of u plus c. Okay, and then from here, I just want to note that arctangent, this is just a matter of notation of x equals tangent to the negative 1 of x. That's the same thing, it's just a different notation in case you aren't familiar. But anyways, now I'm going to multiply this, here, I'll just show you. I over I, which will equal 1 times 2 over I arctangent of u plus c, and then I times I is negative 1, since I is the square root of negative 1, so this will become negative 2i arctangent, and then it's u, but remember, and here I'll go back up, we have u equals e to the ix, so we can substitute that back in, e to the ix plus c. So now we have that the integral equals negative 2 times I times arctangent of e to the ix plus c. And what you might be thinking is, well, didn't we have from earlier that the integral of secant of x dx equals the natural log of the absolute value of secant of x plus tangent of x plus c? And you might say, well, these two expressions, this and this one, are not equivalent at all. But in fact, and I should really be more specific, I suppose, in error, and not really an error, but But something that you should note is that we're taking the real part of negative 2I arc tangent of e to the ix plus c, and that c is written bad, and that does actually equal the natural logarithm of secant of x plus tangent of x, the absolute value of that, I should say, and that equality is in fact plus c, and that equality is true. You can verify it using standard relationships between the exponentials and trigonometric functions. I'm not going to do it just because it's a bit of tedious algebra, and there's not really a use in doing it. But if you don't believe me, you don't want to take it on faith, you think I'm lying to you, you can go into Wolfram Alpha and take the real part of this left side and plug in some value for x, maybe do pi over 3, and then on the right side evaluate the same expression. You'll see that in fact the real part of the left side does equal the right side of the equation. And so yeah, that's basically all I wanted to show. I think this is a really interesting way to evaluate the integral, and it's a lot more straightforward than the common method shown, and doesn't require that kind of magic trick of multiplying by secant of x plus tangent of x over secant of x plus tangent of x. So yeah, thanks for watching. If you made it this far, I hope I hope you learned something new from this, basically, and remember to fall back on Euler's formula for any integrations of trigonometric functions if you're stuck. Thanks.